Okay, so ladies and gentlemen, this is a new interface for me, and I'm going to see how I like it. Miss Revel says it's super fantastic, but I'll let you know what I think of this at the end. Anyways, this lesson is going to be on motion of charged particles in electric fields. Oh my God. Okay, so this is probably the worst interface I've ever used to make one of these videos. Anyways, I'm just going to keep doing it, and you guys are going to have to deal with it. You can blame Miss Revel. So the title of this this lesson is Motion of Charged Particles in Electric Fields. Writing with this pen is like writing with a wet noodle. Anyways, there are two kinds of electric fields that we will look at. The first one is the one you're somewhat familiar with that we've talked about in class, where we have a point charge and we have a field radiating out of that charge. And as we've talked about already, this is a non-uniform field, and you can see that because the field lines move out and spread away from the charge. So let's put down that this is non-uniform. And this is also a lot like gravity around a planet. And you know that when we were doing motion of objects around planets, we had to be careful, and we could only use energy equations to solve for the motion of particles around planets. So in this case, let's just write down no kinematics, only energy. And so now the second kind of field that we're going to look at is actually called a uniform field, and that is set up between two charged plates. So if we hook up two metal plates and we put a charge on those plates such that we have one is positively charged when it's hooked up to a battery, and here's our battery, and the other side is negatively charged, then we end up with field lines running between these from positive to negative, but with some very small exceptions at the edge. You'll notice that the spacing between these two plates, the spacing of the field lines between these two plates, is uniform. So this is a uniform field. And in this case, we can use both kinematics or energy equations. Okay, so let's take a look now at a parallel plate system. And I'm going to set it up just like the one we just drew. And we're going to draw it like this, and we're going to reconnect it to a battery. And we'll put negatives all along here, and we'll put positives all along here. And as I said before, you have electric field lines which move from the positive to the negative plate. Okay? Now, let's talk about if I had a negative particle that was situated right here. Now, the work that would be done on the particle or by the particle to move across this gap would be given by this equation, and it would just be given by the work equation. Work is equal to force times distance. That shouldn't be a shock to anybody. But if we look at that in this case, we have work. Well, we know that work is change in energy, and so in this case we know that this change in energy is going to be a delta EE for electric potential energy, and this is going to be equal to the electrostatic force times the separation between these two plates. And it just so happens that we call that separation between these two plates R. So I know that seems to be a little bit confusing. It's not really that big a deal. But this is how we're going to work with particles moving between the plates, okay? And the other thing that we can look at, we have to remember that there's a defining equation for the strength of an electric field. And that equation was that wiggly E is equal to the electrostatic force per Coulomb. And we can isolate Fe here and end up changing our Fe in this equation to wiggly E times Q times the separation of the plates is equal to the change in our electric potential energy. Now, the other thing that we want to do is we want to take a look at what does delta EE really, how can we measure that easily? Well, we talked yesterday about electric potential difference, and electric potential difference was delta V, we also call it voltage, and that was equal to EE2 per Coulomb minus EE1 per Coulomb. And that EE2 minus EE1, of course, as you can see, is delta V is equal to delta, or change in electric potential energy per Coulomb, which means that we can then isolate for delta EE, and we can end up putting in here that this is equal to delta V times Q. And this makes things an awful lot easier for us, and as you can see, we can cancel out our Q and simplify this whole equation to the electric potential difference across a series of plates is equal to the strength of the electric field between the plates times the distance between the plates. And this is actually a very handy little equation that you can use when solving between two plates. The other form you will see this equation in is just modified like this, such that wiggly E is equal to the electric potential or voltage across the plates divided by R. Please make sure that you don't think that that is a change in velocity. It's not. This is electric potential difference. And it's also called voltage. So when we're dealing with the motion of charged particles in electric fields, we will approach these problems very similar to everything that we've done in the past. And the way we've approached motion of particles in fields in the past is we've started with a statement such as ET1 is equal to ET2. And I think everybody kind of understands that at this point. In this situation, we're going to expand that to say that all the electric potential energy in the beginning plus all the kinetic energy in the beginning is equal to all the electric potential energy at the end plus all the kinetic energy at the end. And I don't think that this is a shock or a surprise to anybody. But what I do want to do is manipulate this equation just a tiny little bit to show you something else here. I'm going to move these terms over to each side. And so what we end up with is an equation that looks like this. EK2 minus EK1. And I'm going to move this over here. So we're going to have E1 minus EE2. Okay. Well, this is easy to see. That this is just the change in kinetic energy. What you might not recognize immediately about this is that that's also the change in kinetic energy, but it's the negative change in electric potential energy. And I don't think that that's a surprise to anybody. What this says is that as the electric potential energy goes down, the kinetic energy goes up, or vice versa. Okay? So that is a very useful thing when we're dealing with these equations, because we can also write it like this. Delta EE is equal to negative delta EK. And as you've noted with what we have just done, you have an equation that talks about delta EE, and delta EE, change in electric potential energy, is equal to delta V times Q. Okay, so this can be a very handy little thing to be noting when you're doing these problems. Let's do a couple of examples. Okay, so here's our example, and I apologize for my writing. It looks like I'm a 4-year-old writing this. Anyhow, here is the question. We have two charged objects. One of them, the one over here that I'm putting the plus signs on right now, has a mass of 0.15 kilograms. And it's located 25 centimeters from a fixed charge. So here's our fixed charge, and you can see that it's fixed because it's stuck on a post. And it also has positive charges on it. And if you can think about this, you know that like charges repel, and so this object will be repelled in that direction away from the fixed object. The charges on these objects are shown, and the question is, how fast is it being that object, traveling when it is finally 65 centimeters away from the fixed charge. We're of course assuming there's no friction or anything like that. So how are we going to do this? Well, let's start off the same way we do all energy equations, where we have ET1 is equal to ET2. And what's all the energy we're going to start with? Well, we can have electric potential energy, and we can have kinetic energy to start. And we could have electric potential energy at the end, and we can have EK at the end. I'll get Miss Revel for this. This is ridiculous. And I'm sure that you can go through and say, well, the object wasn't moving to begin, so we don't have any kinetic energy to start. So why don't we take a look at the equation this way? So we will end up with EE1 will be equal to EE2 plus EK2. And this isn't all that terribly easy, or terribly hard. We'll have K, it's not very easy to make this video, I'll tell you that. KQ1, Q2 divided by R1, which is 25 centimeters, is equal to KQ1, Q2 divided by, that'll be 65 centimeters, plus 1/2 mv squared. And I don't think anybody's going to have any problem working through the rest of this, because this ridiculous pen that Miss Revel has given me to write on this screen, like I said, it's like writing with a wet noodle, or trying to write with a marshmallow. I'm not going to do the rest of this equation because it's grade 10 math. You can figure it out. You simply have to find that v, and I don't think anybody is going to have any hard time figuring that out. So how about we move on to our next problem, which deals with charged plates. Okay, so I've changed my mind. I'm going to show you another example that doesn't necessarily deal with a charged plate system, although it can deal with a charged plate system. So In this example, we have an electron starts from rest, if you can read my grade 2 rating. It moves across an electrical potential difference of 2.0 times 10 to the 4 volts. And the question is, what is the final speed of the electron? And again, we're going to answer this by starting with ET1 is equal to ET2. Now, I've worked you through this a little bit enough that I think that you'll understand what I'm going to write down here, so I'm just going to pause it and do some writing. And so as you can see here, we end up with this statement that the loss of electric potential energy is congruent or shows an increase in kinetic energy. So what it means is that the change in electric potential energy is matched by a change in kinetic energy, or the loss in electric potential energy is mirrored by an increase in kinetic energy. So what that means is this negative does tend to bother grade 12 students. That doesn't need to be there. It just means that this magnitude, the magnitude of this, is equal to the magnitude of that. So we have already talked about the fact that a change in electric potential energy is equal to the electric potential difference times the charge, and that will be, of course, equal to 1/2 mv squared. Now this will be v2, but ek, sorry, when we did delta ek2 will be this term, which is exactly what we want to find. ek1, of course, will be 0 because the electron starts from rest, so we don't need to put it in here. And I think the only other thing that I have to tell you here is you need to know what the charge is you're dealing with when you're dealing with an electron, and the charge on an electron is 1.6 times 10 to the negative 19. And so that's all you have to worry about when you're doing this question. I don't think that you need me to work any further through it, so I'm just going to stop this right now. Okay, so first thing I will say about the homework is don't panic. This is one of the more difficult topics in this course. And I would suggest that you struggle with this homework, and when I see you again on Monday, we will certainly take it up, and I will answer any of the questions you might have. So take a look at page 368, make sure you do questions 1 to 4, and 371, make sure you do questions 1 to 4 as well. I would strongly recommend at this point that you are filling in the mind map that we started for electric fields, or that you should have started for electric fields, and if you haven't started one, I would grab a sheet of paper now and begin.